Welcome. This is Optica Corporate Engagement, and it is a webinar proudly presented to you by the Bertin Alpao. For those of you who are with us for the first time, I'll describe a little bit the dance. So the entire webinar is about 1 hour, and the first part of the webinar is the presentation from our host, Bertin Alpao. The second part of the webinar, about 15 to 20 minutes, we will devote to the questions from the audience. Because of this, please listen carefully, and if you have questions, post them into the chat. The questions will be either replied by the team of the Bertin Alpao in the chat, or I will read out them later after the presentations are complete. And with this, we can go live. I would like to present to our hosts for the seminar today and to say just a couple of words about Bertin Alpao. Alpao has been developing adaptive optics since 2008. And now, as a part of the Bertin Group, they continue to develop adaptive optics and also deformable mirrors, and the control software that is used in the variety of imaging applications across different industries. Today, we're fortunate to have their Chief Scientific Officer, Julien Charton, with us to present their newest solutions and also to discuss together with the guests how their solutions are helping to address the demands of most tough applications in the life sciences. Julien, the floor and of attention of everyone is yours. We're ready to roll.
Thank you, Olga. I am in charge of innovation at Bertin Alpao, and I am very happy to present you the first new product we have in this webinar. It's about a deformable mirror with integrated drive electronics. So I will share my screen and start the presentation. Is it okay? Okay, great. So this is the first product we will introduce now. And so let me introduce and say why we decided to develop this new product. The first idea came from a completely different application for adaptive optics, which is astronomy. In astronomy, we are providing deformable mirrors with a large number of actuators, much larger than we usually use in vision science or microscopy, for example. You have an example here in this picture. This is a deformable mirror we delivered to the Keck Observatory. So this is one of the largest and most famous telescopes. And with this kind of device, you see the back side of the deformable mirror. You have a large number of connectors and cables. You see about 1/3 of them, and you see that it's quite complex to route and to manage all these cables. And this is on the deformable mirror side. So you see that it sits on an optical bench. But if you go to the other side of the cables, you see the electronic cabinets, and you see that the cabling is really difficult to manage. So we thought about this problem and said that, okay, we have to find a solution to somehow integrate the drive electronics into the deformable mirror itself to remove all this cabling mess and to make something that is much easier and to use and much more compact. So this is for large deformable mirrors for astronomy, but actually the first product that we are happy to introduce is a much smaller one because this kind of improvement can of course benefit to other applications. So what is the life science version of this integrated drive electronics? What you see on the screen now is up to now the most compact version of drive electronics we had for our products. So it's a small box, but still it is almost 300 millimeters in size. And you have still some cables and connectors to plug in from this drive electronics to the deformable mirror. So what we managed to do is to fit exactly the same performance of drive electronics into much smaller electronic boards. So you see they are just sitting close to the largest OEM box. So they are you see just the two small boards that we have now, and the only interfaces and the only cables you have is a Ethernet port and a power connector. And you see some euro coin just to have an idea of the size of everything. So the benefit of this, of course, is that now we can put all the drive electronics into the device itself. So what you see here is a deformable mirror with a 97 actuators. So before we had only the front part and large cables at the back side, and now everything is inside, and you see at the back side you only have these two power and the Ethernet interface. And just to mention that if you prefer to use USB, for example, because you don't have a spare Ethernet port on your laptop, for example, it's very easy to just use this kind of dongle to connect using USB. So what are the benefits at the end of the day of this product? The idea is that you get exactly the same performance, optical performance, deformation, amplitude, and speed as a standard DM97, which is a de facto standard deformable mirror in life science, for in particular for ophthalmology and microscopy. But on top of that, you have a much more compact product. You have a very simple Ethernet interface. It's compatible with any operating system. Can be Windows, Linux, macOS. You could even use a Raspberry Pi or any device with Ethernet capability. And you don't need to install any driver on your computer. Of course, we provide some libraries and examples to help you interface with a deformable mirror, but it is not mandatory. And what you see on the picture on the right is the integrated graphical user interface. There is actually a small web server running inside the small drive electronics, and you can connect to it as soon as you plug the Ethernet port to your computer or to your network. You can connect to it, and you see, I won't go into the details, but maybe you have some questions, we'll answer to it later on. But you can put some Wernicke modes, you can see the shape of the deformable mirror, you can control the offset or the bias shapes that you want to use. And really the idea is that you will get your first Wernicke mode less than 1 minute after you unpack the product. This is really the idea to make it easier to use. So now I'm very happy to introduce Zoran Popović from the Profundus camera that will show what kind of application can use this kind of product. And this example is about ophthalmology and vision science. Thank you, and see you later.
Thank you, Julien. Can you stop sharing so I can take over? Thank you. And let's see. There we go. So thank you for inviting me to this meeting, to this tutorial. Thank you, Bertin Alpao, and thank you, Optica, for inviting me. I am Zoran Popović. I'm co-founder and chief scientific officer of Profundus AB, which is a company based on the west coast of Sweden, developing a multi-conjugate adaptive optics retinal imaging flood illumination camera. So what I'm going to do today is talk to you slightly about what is the part of adaptive optics in ophthalmology and ophthalmic imaging, what has been done, what is happening today, and what are we doing. And just to open your eyes, I always like a bit of history in my talks. The topic we're touching on today was already discussed by Sir Isaac Newton back in the 18th century, so it's not a new topic. It's just that we have some more tools and power at our hands so we can actually do something about it. And the more modern version of this topic was addressed by Horace Babcock in the 1950s, when he first worked and published his pioneering work on the principles of adaptive optics. So it all started out by that time, Horace Babcock's publication, and then the US military basically put a lid on this for a few years until it surfaced during the 1980s. And today the technology is used in many applications: astronomy, laser communication, optical fabrication, both low and high power lasers. It's used in microscopy, and the topic that I'm going to address today, retinal imaging systems. So what is the role of adaptive optics in retinal imaging, and why do we use it? It basically works in the eye as it does on sky. If you're familiar with the astronomical part and use of this, we need information about the turbulent medium that we are going to correct. In our case, it's the optics of the eye. The way to get to that is to actually use a probe beacon to create the light point in the back of the eye, which is on the retina, and that light then shines out through the eye, through the adaptive optics system that we have, passes the deformable mirror, and is analyzed by a wavefront sensor to find out what corrections we need to apply. They are calculated by a control computer, and this all works in closed loop. So by iterating this measurement and doing iterative corrections with the deformable mirror, we can correct an aberrated wavefront and ideally have a plain wavefront that will give us extremely nice and high resolution on a retinal camera. And that's all good in theory, but you cannot always reach all the way. Because we have a system in the eye that's quite complex. We have a lot of different surfaces that are affecting the optics of our imaging. We have the cornea, but before the cornea, we actually had the tear film, and the tear film constantly changes in shape. It is applied by your eyelid, and then it dries out and reapplied. So that is a medium that will constantly be changing. And then we have the optical lens of the eye, which also has what is called accommodation. It can focus. So that also changes over time. And then we have our breathing, we have heart rate, we have a lot of factors influencing the ideally statical medium that we are trying to correct. So we have something that requires an iterative closed loop correction. In addition to that, we have a target that we want to view, which is the retina. And the retina is just not one piece of optical or biological material. It is a very complex structure of various cells in various layers that make up the construction that we call the retina. The retina is built up backwards. If you compare it to a digital camera, the digital camera has a lens, and then you have a CCD. Our CCD, the retinal photoreceptors, are at the back of all of this. In front of that, you have all the wiring and the connections that you need to be able to see something. So it's a backward design. So at the back, we have the photoreceptor structure. At the front, in a normal eye, we have the vessel structure. In between, we have mostly invisible media, but in there, we can sometimes find structures that we are interested in, and also disease structures that might be interesting to look at. And you can see the size of the structures we're trying to image in ophthalmology. It's from 2 microns approximately and up to maybe 10 microns, which is, anyway, this is all well below the optical resolution capability of current imaging systems without adaptive optics. So what are the benefits? It's pushing the limits of imaging in the eye from today's maybe 15 microns, let's say, in non-adaptive optic systems, down to below 2 microns, actually, in the best optical lab-based adaptive optic systems that are around. So what that gives us is the potential to provide information about currently subclinical information about retinal disease and facilitate a lot of good things, which is either earlier or improved diagnosis of disease. It's detailed or long-term follow-up of disease progression, and also detailed follow-up of medical treatments effects. So today, we, in many studies and in clinical practice, you do not have the ability to actually see what's happening on the retina when you apply certain treatments. You just suppose something is happening and then evaluate that using indirect methods that are usually quite blunt and don't give you detailed information about the biological processes that are happening. But this technology can actually give us tools to actually see what's happening, and that's a huge difference. So if we look at imaging of normal retina, what are the structures that we expect to see? So we, in traditional lab-based and study projects that have been conducted, a lot of people have looked at the cone mosaic at various positions, either centrally or peripherally, just trying to understand how is the basic buildup of the structure in a normal human eye. This has been done in lab situations before using a microscopy on enucleated eye material, but now we can actually do this in live eyes, which is quite a difference. We actually don't have to pick out eyes from people anymore. We can do it and let them go home and still see. So either the cone photomosaic or rods as well can be viewed through this technology. There's imaging now, not just using autofluorescence, but also using indirect illumination of the RPE mosaic in human eyes. We can visualize the smallest vessels and capillaries of the retina, which can give interesting information about what's happening in a diseased versus a normal eye. So this is all normal eyes. And then there's also ways of, this has been shown by several authors, but primarily it started with Austrian Roda back in 2011, where you can actually do functional imaging. You can stimulate individual cells and actually map out which are red, green, blue cells, long, middle wave, or short wavelength sensitive cones. And you can also actually do microperimetry, which is analyzing function of retinal cells using this kind of technology. And then there's also the push to introduce this in other technologies. OCT stands for optical coherence tomography, and what that gives you is a three-dimensional volumetric imaging of the retina, which you can then turn and twist and look at from different angles, but it also gives you information then structurally about the retina in cross-section. So it's like ultrasound, but with light, so ultralight imaging, for those who want to get a grasp of what that technology is. And this is all well, but all these lab-based high-resolution systems have one issue, and that is it's still lab-based. So what we try to do is to get this out into using this for not just research, but also applied clinical use. And there is a push of investigating a lot of different retinal diseases. There's a plethora of them out there. The most common ones I've listed here, I won't read them all out, but that's just for you to see that there's a lot of work being done on diseases that can gain knowledge and information by using adaptive optics to reveal the more intricate details of disease progression and also how it starts, maybe. But like I say, all this is well and good, except that today there is no clinical use of adaptive optics that is widespread. So very few clinics do have adaptive optic system. Most don't. One of the key issues is that many of these lab-based systems have very small imaging fields, corrected imaging fields. So this is an example from a quite recent paper this November this year, where they've analyzed the normative densities of cone photoreceptors across the horizontal and vertical meridian in an eye. And the imaging field is 1.2 by 1.2 degrees. And you're trying to do this over a wide field of retina, which in standard clinic, if you take a fundus image with a traditional camera, it's 40 degrees. And if you want to cover 40 degrees with a resolution or a field of view of 1 degree, it's going to take you a lot of time. So clinically, this doesn't make sense. And that's where I'm now going to step over to say that how can you overcome this to push this technology into the clinic? It's by using a larger corrective field of view. And how do you do that? Yes, you can use what we are using in Profundus. It's multi-conjugate adaptive optics imaging. It will give you a larger corrected field of view that gives you a sense of, if you look at the left image, the background image is what I just showed you. The dashed line is the size of one of the images from our camera. So in one shot, you actually cover quite a large portion of the retina. So in one shot, we cover the clinical macula of the eye. And by extrapolating that, you can quickly cover larger areas by just doing imaging further out and create a mosaic. So you can cover large patches of retina in a much more quicker way. This is just 5 images compared to, I don't know how many images were in the image of the slide before, but this will give you a tool that is probably more clinically useful than earlier instrumentation. So how does multi-conjugate imaging in the eye work? What we do is we, instead of measuring like other instrumentation, measuring the aberrations in one direction using one probe beam and one guide star, if you could call it that, on the retina, what that gives you is quite a local correction. Instead, we measure aberrations in 5 directions using 5 beams, and we use 2 deformable mirrors to correct these aberrations. So what we have to start with is measuring aberrations in 5 directions, and we've developed a multi-reference wavefront sensor that actually allows us to capture 5 Huck-minograms on 1 CCD and do that. Instead of having 5 cameras, 1 per beam, we have 1 camera covering all 5 beams. And then we have 2 deformable mirrors from Alpao in our system. One pupil mirror, which is a converted 97. It's a 57 currently due to the optical design of our instrument. And we have a field deformable mirror, which is the EDM 97 that covers and takes care of field-dependent aberrations. And if you remember the image I just showed you in the slide before with 5 colored areas on the retina with the beams covering that, that is basically the footprint of the beams that you will get on the field deformable mirror. So that is what we use to correct field-dependent aberrations. The pupil EM corrects pupil aberrations. And in the system that we're building, we are using the EDMs from Alpao because of the advances of this technology. Like Julien just told you, there is no cabling now, there's no external electronics. So we were able to integrate all of this into one system. And what we can do with this is previous work from our group with our previous versions of this camera. So what this just gives you is an indication of, yes, it's a wide field of view. This is this paper where we described how we could analyze the capillary density around the avascular zone of the central fovea. And this is also just an application to show you that with just a few images, we can actually cover quite some large areas centrally on the retina and obtain much better images and much higher, much more information and better quality than is possible with current clinical technologies. And this is then the camera that we are in the process of CE marking right now, which uses the Alpao EDMs. And as you can see, the only external box we have today is a computer. Everything else is integrated inside the camera. And that is thanks to the current EDM design that actually allows us to gain ground and to be able to integrate this in a compact desktop system. So with that, I just want to tell you that, yes, we are doing multi-conjugate adaptive optics. There are some other guys doing that in Chile, but they have a much larger instrument than we do. And hopefully our instrument can fit in the clinic, which theirs cannot. So thank you for listening and thank you for your time. Julien?
Thank you, Zoran. Okay,
stop sharing. There you go.
Perfect. Okay, so now I will talk about a completely different technology, but that can be used for the same kind of application. And so I will share my screen again for the presentation. Just one second. Okay, you can see my screen. It's okay? Great. So this completely different technology, which is also very new, is what we call the thermal SLM. SLM stands for Spatial Light Modulator. So probably a lot of you know already this kind of device, but I will introduce them again, just that we are all on the same page. And of course, then talk about this new version of SLM that we are introducing at Alpao. Let me get the pointer. Okay, so what is SLM? So the rigorous definition is that any device modifying the homogeneity of a light beam can be called a SLM. So a deformable mirror or LCD screen or even a DLP device can be seen as a SLM. But of course, for most people, for almost everybody, what they call a SLM is actually a liquid crystal device modifying the wavefront. This is what is used in the field of adaptive optics and wavefront control. So we have just a few images of existing commercial SLM, not from Bertin Alpao, but you always have an optical active device and some drive electronics to control it. So how it works? Most products available on the market are based on the LCOS technology, which is liquid crystal on silicon. So I won't go into the details. The idea is just to explain how the existing product works, to see the difference with what we are proposing. So you have a set of layers. At the bottom, you have some CMOS, it's a kind of electronics that will control the pixels, and the active layers, you have some electrodes, and you have this layer of liquid crystal, and this very specific material has a different index of refraction depending on the orientation of the molecules. And when you apply an electrical field, so when you apply a voltage between the two electrodes, then you will change locally the index of reflection and polarization performance or response of this device. So the light will come from the top, will go through this glass like a window, and if it's correctly polarized, then it will go to this to the back where there is some reflective coating, and go back to the, let's say, the application with a different wavefront. So these devices are very useful. There are many vendors around. I just made a table. I won't go into the details, but just to say that they all have different kind of performance. Some are faster, some are larger, some have a lot of pixels, some have a different kind of stability and response. The most known in the field of research and adaptive optics are probably Hollow-Eye, Hamamatsu, and Middelrock. And these components are already used by many in many applications. So the goal of Bertin Alpao, of course, is not to do the same, because these devices are working well, and they have been developed for decades by these companies. So of course, it's not useful to do the same. But if you look at the benefits and the drawbacks of this technology, the benefits, of course, are you have the high resolution. This is because it's similar to the LCD screen. So they have resolutions that are similar to VGA or FGA or the kind of resolution you have on your computer display. So a large number of pixels. The cost, or at least the cost per pixel, is relatively low. It is compact. The size of each pixel we saw in the slide before, it's a few microns only, so you can have a lot of pixels in a small area. It's not always a benefit, but for most applications in life science, it's good because the beam size are relatively small usually. And another benefit is that there is no mechanical part. There is no really moving part. So in terms of reliability and sensitivity to vibration or environment, tough environment, it's a good part. So our idea was to keep all these benefits, but to try to minimize or to remove some of the drawbacks. The drawbacks are, again, it's for most, it's an average SLM drawbacks. Some are better or worse depending on the vendors, but it's a relatively low laser-induced damage threshold. This is due to the sensitive materials that are in the device. The reflectivity is not very good, as it is dependent on polarization. For example, if there is no specific polarization on your light, on your beam, you lose half of the light. So it's a real drawback for many applications. As I said, it's only for small size, so if you cannot easily adapt it to the size of your optical beam, and the stroke or the modulation amplitude on the wavefront is small. It's most of the time it's not larger than 1 lambda, so you have to use many tricks if you want to correct for larger aberrations, for example. And due to the drive electronics, there is some refresh rate on the full array of pixels, so you may have some kind of flickering, so small amplitude, but global vibration on the wavefront. And again, depending on the applications, this can be critical. For example, if you are looking at very high contrast or high resolution instrumentation, then this flickering effect, even if they are small, may be a complete showstopper. So the part that we want to address is mainly these parts. Just to mention that the laser power won't be much larger than compared to a standard LCOS SLM, but we think we can really improve all the other drawbacks of the standard SLM. So what is actually the technology? It's completely different, even if we call it SLM, because everybody knows the name, or most people know the name already. But the physical effect inside this device is completely different. There is no liquid crystal, there is no electrical field. What we are using is the thermo-optic effect of the material. So this effect is present in any material. If you are doing some high-performance optical design, you know that the index of refraction and the focal length, for example, of the lens will change depending on temperature. Normally, you try to minimize this effect to make an optical design that is very stable. In our case, we will try to increase this effect. And the idea is that, imagine you have a layer of material with a large thermo-optic effect. You have a light wavefront coming on one side, and so it's a device in transmission in this example. If you can change locally the temperature at some point inside the material, then the index of refraction will change, the speed of light will change, and the wavefront at the output of the device will be modified. So this is a very simple principle. This has been developed at the beginning by the UFU Institute, so it's an Institute of Photonics and Electronics in Prague. And you can also imagine a device in reflection, like for standard liquid crystal SLM. If you put a reflective coating on the back side, then you can have something similar to a deformable mirror. Just to mention that you can use a thermo-optic effect, so the change of index of refraction with temperature, but you may also use a thermo-mechanical effect, which is a thermal expansion actually, that will also change the optical response of the device. So the principle is simple, but of course the key is can you really locally change the temperature inside this layer, and can you do it reasonably fast? Because in the common life, when you try to hit something, after a while it's very slow, and after a while everything is hot. It's not easy to have a very specific part at a different temperature. So there is a trick to do this. So this is a simulation of the same kind of material layer we had in the previous slide. So you see the input wavefront is coming on one side. Then you have the hot point that you try to generate in the middle of the material. And from this simulation, you can see the effect on the wavefront at the output of the device. And this is without any trick. And you see, as I say, that after a while, everything, the temperature gradient is expanding and to the infinite, actually, or to about the edge of the substrate. There is no limit. This is not what you want. And it is quite slow. It starts quite a bit fast, but as soon as you start to hit a lot of material, the thermal inertia is becoming very large, and your wavefront profile is drifting forever, and you can get this kind of profile. So maybe you can do some kind of focusing lens with this. This is an application, but it is not very useful, and you cannot use it like a deformable mirror or SLM for adaptive optics, for example. So the trick actually is that if you take your active material, but on each side you put a very high thermal conductivity material, then again this is a simulation, but it's very close to what we get in the real prototype. Then somehow you can make the hotspot much smaller, and because it is much smaller, the dynamics is much faster. And by tuning the layers and the thermal property and thickness of each layer in this example, you can tune the amplitude and the speed and the width of the response of on the wavefront. So it's a bit like if you have a SLM pixel or deformable mirror actuator, but the difference is that the material is continuous, and just by engineering the layers in the global device, you can change the amplitude and size and of the response of each, let's call them pixels or thermal pixels. So this is the trick to get what we want at the end. And the question is about the dynamics. How fast and how can you tune the speed, the response time of this kind of device? So you may know that all thermal devices or systems can be have an electrical equivalent that can be used for simulation. So you can modelize the heat flux by a source. You see in this electrical circuit, the thermal capacity is like an electrical capacitor, and the thermal leak that will be introduced by the high thermal conductivity layers is like a resistor. And based on this very simple electrical model, you can use electrical simulation tools to see how fast you can get and what is actually the response of this system. So there is no surprise. This is a first order system. So if you instantaneously put some heat flux somewhere, like a pulse of thermal power inside the device, then the global temperature, which will give you at the end the effect on the wavefront, will slowly or will increase depending on the thermal constant of your device. And then when you stop to hit the dot, the spot, then the temperature will slowly decrease. And of course, if you tune the parameters, you can get it faster or slower. One key, and this is why I show this model, is that it's not really symmetrical, because there is a trick. If you want to go very fast, maybe you can just use a very high power laser or something very powerful to have a lot of power to hit very fast your layer. This is what you get here. You go very fast and you stop hitting. So in one direction, this is very fast, but then you cannot cool faster than due to the physics. So the cooling phase will be slower than the heating phase. So it's important to understand the trade-offs that we can make on the device, and this is due to the physics. And for those that are not familiar with electrical models, there is a very useful model. It's an hydraulic circuit. If you imagine a bath and some water pouring on the top, and then you have exactly the same effect. Maybe you can put a lot of water to have the level of water increasing very fast, but it will decrease only due to the leak, and you can do nothing about this. So at the end of the day, it is important to remember is that the response time of the device will be proportional to the phase amplitude that you want to do. So if you want to do 1 lambda only, it will be faster than if you really need to do, I don't know, 10 microns of deformation because you need this for your application. And it is also, you divide this by the heating power. So if you can hit very fast, you can tune the parameters and the leak to have a very fast response time. But maybe you will have a global power budget, or the system will be very large, or maybe you will become to have some safety issues if you have a large laser, for example. And if you have to reduce this power, then the cost is that the response time will increase. Now, what kind of results can we obtain with this technology? So the first example was obtained by the UEFI laboratory in Prague. And what they do is exactly the same principle as I presented. It's a device in reflection, and the application is for microscopy. So what they do is they put some heat map on the device. So this is a very small device. It's a few millimeters across, and they can obtain a programmable vortex that is very useful for some microscopy application. And you may have some, if you want, a lot of more details in this paper by Adrian Robert. So this is the result that they got in the lab. And at Bertin Alpao, based on these ideas, we developed a new device. So this one is in reflection because it's much easier and much more compact as a first product. So this is why we chose this option. And what we are using is optical driving to hit the device. So you see the schematic here. If you are using a laser or a high power LED, high power is like a few watts. It's not a megawatts, but it's to give you an idea. And if you are using a DLP chip, like the one you have in a video projector, for example, then you can project an image, whatever image you want, onto the optical layer. And because you have a high power LED at the beginning, you can create this temperature map on your device, and this will be transferred into a wavefront map, a programmable wavefront map on your optical beam, exactly like a deformable mirror. The difference is that the principle of operation, the physical principle is different. There is no moving part, we are acting on the thermal properties of the material. So what you see on the right is an idea. So the CAD drawing of the first prototype that we are working on now. So you see in the box is mainly the DLP projector and module. And the active layer is actually quite small. It's 5 to 10 millimeters across. And this is so at the end of this cylinder, this is like a deformable mirror. This is the part that will be optically active and that will reflect the optical beam to change the wavefront, to correct for it or to generate some interesting shape on the wavefront. So what kind of results we got from this prototype? So the first unit we have has a very important amplitude of deformation. So what you see here is a wavefront, directly the wavefront we measure. So we create a temperature map that is like a square, and as expected, we can see a square shape on the wavefront. It's open loop. It means that there is no feedback to control this pattern. So it's showing also that the device is quite linear. There is no difficult calibration to do for this kind of simple shape. And the amplitude of deformation we can have is 10 micron, which is very large compared to standard SLM, for example. And the next important part for this kind of device is, okay, what is the best optical quality you can obtain? So in this case, you have to operate in closed loop. So we have a wavefront sensor, like the one measuring this pattern, and we are using it to try to minimize the wavefront map and to have the device as flat as possible. So this is a temporal response. So this is for the PV and the RMS wavefront errors that we measure. So we start with the bias shape of the device, which is 1 or 200 nanometers RMS across the pupil. And when we close the loop, slowly we can, in a few iterations, we can reduce this error, and the best flat we can obtain, so giving you an idea of the best optical quality, is 7 nanometers RMS. There is a difference with this device compared to standard SLM. A standard SLM really has pixels. They are physically divided inside the device. You cannot change them. So when you activate one pixel, the neighbor pixel is not moving at all. There is virtually no crosstalk on the best device, at least. In this kind of thermal SLM technology, it's a continuous surface. So it's very good because there is no diffraction effect, there is no pattern on the mirror or on the wavefront. But if you want to control the device very accurately, you have to calibrate this. So if you do a full 3D FEM model of the layer, so you see this is where we will hit the layer that is in between the very high thermal conductivity layers, you will have this kind of thermal response, and it will give you this kind of response on the wavefront. And you see that it's close to a rectangular shape, but not exactly. So it means that if you want to do any wavefront you want, you have to go through a calibration process. So I say this is done at the factory. This is exactly like for deformable mirrors. So for those that are already using deformable mirrors, they will not be surprised because this is exactly the same. But for those that are used to SLM only, you have to understand that you cannot send directly the pattern or you want to the DLP device. You have to use a calibration matrix that we will provide, of course, with the device before you can get any wavefront you want. So this is just a way to say the same thing. So if you have a target wavefront, for example, a Wernicke mode with astigmatism, you have to combine this with the SLM calibration data that we do at the factory. Then you have a map that is not exactly the same as the Zernike mode you want to do. And this way, you will have the actual wavefront, and that is very close to the target wavefront you do. But you have to, we will provide a library that will do this job for the end user. So about the first samples we have. So the current prototype we are working on is in this column. So as I said, there is more than 10 micron of wavefront modulation amplitude. The response time is currently not fast. It is related to this very high amplitude. So it's around 200 milliseconds, depending on how exactly you define it. The spatial resolution is around 50 by 50 pixels, so it is not limited by the addressing device, but by the minimum size of the thermal spot you can create into the active layer. Compared to a standard LCOS SLM, we already have a very large spectral bandwidth. So there is no condition on wavelengths within this range, of course, or polarization or monochromatic light. You can use any light you have with the device. And the optical configuration for this device is in reflection. So we have to deliver to the first prototype to the University of Bern very soon, and we can duplicate it. It's not yet a real completely finished product. We call them samples, but they will be available beginning of next year. And the next step, well, it will depend on the demand. So because we can tune the parameters, and of course, if you prefer to keep the large amplitude or increase response time or reduce the response time, we will not do the same tuning. But currently, the baseline is to have the first product with a smaller amplitude of modulation, because it's what the SLM user needs, and to reduce the response time below 10 milliseconds. We think we can go close to 1 millisecond, and to increase a lot the spatial resolution, so you can do a more complex wavefront. We can tune the aperture size. The first device, the goal is to have a 10 by 10 millimeter pupil, and keep the same spectral bandwidth for the reflection device. And we also are working on the transmission device, because in some application it's more convenient. But again, we would be very happy to have your feedback and to see what kind of parameters we should work on in priority.
Perfect. I believe there will be quite some requests to you. And exactly with this one, thank you very much, Julien, for the presentation. Very much. Thank you very much, Zoran. And let's take a couple of questions. We have a couple of them in the chat. And from the order of the presentation, Zoran, there is a very interesting question addressed to you, which asks, so for each person, the retina imaging has different aberrations. So you will need for each person, of course, to take a different image. And so how fast does the wavefront sensor measures the wavefront, but rather in the sense, you know, the entire feedback loop, not just how quick the sensor itself is, but how quick the entire system is.
The closed loop frequency of the system, it measures and corrects aberrations at a rate of about 14-15 hertz. So independent of any eye you use it, it's going to run at 14 hertz.
And could you comment, maybe elaborate about the routine of the basically how it's called nulling the sensor, so calibrating the sensor?
The calibration is a standard calibration. We do it internally in the instrument, so we do not need to add parameters or use any devices outside of the camera. So the calibration is internal. And we do both the traditional calibration, that is coupling of the wavefront sensor to the mirrors, and then we also perform an uncommon pot calibration to optimize the image quality on the imaging device.
Thank you. There's another question. Well, always a classical question. What is the cost of the Profundus large field of view imager? Or more practical, does it also do split imaging? And how are two mirrors used?
Split imaging, we do not do. The cost is the answer you always get back. It depends, and we actually have not set a price tag yet. But come back during spring or in half a year, and we will be more able to answer that question. And then the last question was, how are two mirrors used? So again, one mirror is used the same way as in all other adaptive optics instruments or devices for retinal imaging. It's a pupil deformable mirror. So it is placed in a pupil conjugate plane. The other mirror is placed in a conjugate plane that's virtually inside the eye. And that plane is chosen so that we have an overlap of the beams that intersect from the different guide stars or guide points that we have on the retina. And that is to maximize the coverage of the volume of the retina that we are actually measuring aberrations from.
Thank you, Zoran. Maybe a curiosity question from my side. What is the most critical parameter that made you go for the solution from the Bertin Alpao?
I think that's for me or for us, it was actually the diversity of sizes, the range of different mirrors. So you can actually customize, you can build the system you want, and then you choose a DM that suits your needs instead of selecting a DM and you have to build your system around it. So for us, it was quite easy.
Thank you very much. I mean, Bertin Alpao is famous for their custom tailored solutions. Julien also questioned a couple of questions for you. Thank you for a nice presentation. In regards to the thermal special light modulator, which laser power is needed to cause thermal optical effect, and is it comparable to the laser power at which LCOS react?
Okay, so in our new SLM technology, actually you may have two different lasers. So the first one, of course, is to create the thermal effect. So it is inside our product. In the current prototype, it's a few watts. If you need a larger pupil or if you need a faster device, maybe we'll have to increase the power. It can be LED or a laser, so depending on the technical details of the addressing we need. So this is for the driving laser. And there is also maybe a laser that the customer will use on this device. And as I said, there is a maximum power. It is not clear yet. It will depend on the reflectivity and the coating we put, because of course, as we are sensitive to thermal effect, if you want to use a science beam or an application beam with a high power, it will hit the device itself and change the wavefront. So it will, of course, it may become unstable for your application. But so to answer the question, it's 5 to 10 watts, but it is inside the box.
Do you have any preferred wavelength at which you which you like to use to modulate the lens?
So inside the box, yes. Because we may use some materials that are absorbing. What we want to do is to absorb the power of the laser to hit the material. And so to do this, some materials, of course, are absorbing at a particular wavelength. So we will use these wavelengths for the lasers.
But for now, you don't have a preferred one that you would say it's always 1030. Okay. Thank you very much. And I think with this, that were all the questions. And I would like to thank once again our speakers, Zoran and Julien, and Bertin Alpao as our host. And yes, hope to see you for the next webinar. Thank you very much, everyone, and have a lovely evening.